Good morning, students.
Good morning, sir.
The last class we have done some shear force and bending moment problems, and now we will discuss theory of bending. This derivation is very important. That's why I am taking this into your consideration. And whenever you are studying for the series examination as well as university examination, this will help you a lot. Hope you were well set for the upcoming series examination. And currently, the first series examination was not as I expected because some students may miss some data. That's happening continuously now also when we are doing a problem. You feel you can understand that you are knowing the answers, you know the steps, but still you are not able to reach the answer. So that's a problem. This will be continuing in your series examination also. Maybe the same problem may be affected in series exam 2. So be careful. You cannot study the subject by reading it. You have to do by yourself in a paper. Take a problem, you have to write the steps and compare the answers, whether you are getting the answer or not. Then only you will understand it. 3 and 4 modules are in the second series examination. So study both those modules in the first module, that is third module. The main important given to the side which I have taught you, that is shear force and bending moment diagram, then theory of bending, वगैरह वगैरह. Then in fourth semester, sorry, fourth module, deflection will be there, McClay method will be there, strain energy methods will be there, Castigliano second theorem will be there, reciprocal theorem will be there, and problems according to all of this will be in your second series, whatever we have discussed. And no proof is required for Castigliano and reciprocal theorem. These are the important area the question will be asked you in the second series examination. So theory of bending is one of the important area which we should focus on. So for that, first of all, we must know, don't write it because we have already gone through the notes. So we will just discuss all the points. This is only for your reminding or revision. So simple bending or pure bending. They both are same terms, that is simple bending or pure bending. The question may be asked, what is simple bending? In other ways, they may ask, what is pure bending? Actually, the answers are same because that is the term. And when an external force, this is the important thing, when an external force acting on the beam, there will be shear force and bending moment. We have already discussed how to draw shear force and bending moment equation, bending moment diagrams. But when a beam is subjected to external force, that is, you can see a point load, UDL, or continuously variable load, the shear force as well as bending moment are set up in all sections of the beam. Okay. Due to that SF and BM, the beam will be undergoes deformation. Okay. And the beam offers a resistance to that deformation known as bending stress or shear load. And stress induced due to bending moment are known as bending stress. So when we are applying an external force on a beam, there will be shear force as well as bending moment. But the stresses induced by bending moment are only considered as bending stress. So we need to think the shear force acting at the section is equal to 0. Then only we can say there is a pure bending. That is, I have written here. when a length of beam is subjected to zero shear force. This is the important point. When a beam is subjected to zero shear force and constant bending moment, then that length of the beam is subjected to pure bending. It's a very important statement. The shear force is zero for a section and bending moment exists, that is a constant value, then the length of beam is subjected to pure bending or simple bending, not bending. There's a mistake, 1 minute. This is P, not P. Simple bending. For that, I have taken a section AB. You can see a section AB overhanging about point C and O. So we are applying a load W here, and A and B are having a support, and O is having another value, that is W equivalent to this value. So when you are calculating, you will find it as RA equal to W and RB equal to W, because AC and BO are same, that is small letter a. The length BO and length AC are same, that is small letter a. So when you are taking moment about A or B or any point C anywhere, you can directly find out that RA equal to W, RB equal to W. Okay. And when you are applying, you can draw the shear force diagram of the same. When you are drawing the shear force diagram, here force is right hand side onwards you will do. Here W is acting on the point O, that is in downward direction, so that is positive. So this will be positive. So there will be a positive W rise from point O or D. Definitely it is better to decide it is D. Okay. And when comes to B, you can see that there is no intermediate load here. So definitely this will be a horizontal line till B. But there is a support reaction, that is W, acting in the opposite direction to the force at D. So when you are taking like that, when you are taking like that, W minus W, that will become 0. So at point B, there will not be any shear force. And from B to A, when you are looking, there is no intermediate load, no point load, no UDL, no continuously variable load. And so from A to B, there will not be any shear stress or shear force. And look at the point A, you can see a support reaction W, which is acting towards upward, so that will become negative. So there will be a negative W, as well as from A to C there is no intermediate load, so definitely there will not be any load. So that will be a horizontal line till C, and when you consider C, there is a downward force, that is positive W, and obviously here there is negative W, so cumulatively that will become 0 at C. So when you look this figure, you can see that from A to B, that's the simply supported beam area, there is no shear force acting. And now you need to draw bending moment diagram. When you are drawing the bending moment diagram, you can see that the bending moment diagram will become an incline from O to B. When you are substituting the values of W, you can see that here x is 0, there is no length change, so this will be 0. Till now, here, that is at point B, that will be W into small letter A. Bending moment equal to W into small letter A. And when you are going further till A, there is only load axis will be W into A plus L and W into minus W into L. So cumulatively you will get W into A, right? From here to, because of this one, this is clockwise movement, so definitely that will be negative. W into taking moment about A means W into A plus L and minus plus W into L. When cancels, you can write it in your paper and you will see that the moment at point A will become W into A. So this will be a horizontal line. And after that, when you are calculating at point C, bending moment will come 0. So considering A to B section, that is a simply supported beam section, you can see that there is no shear force as well as there is a constant bending moment. You can see that a constant bending moment. This is known as pure bending. Okay, this is known as pure bending. When in a section there is a zero shear force and constant bending moment, then the length of beam is subjected to pure bending or simple bending. That is what we have seen here. I have explained all these things, so no need to explain further. So hope you can understand this one. So after understanding simple bending, we need to have some assumptions for theory of pure bending. We are going to discuss theory of bending. For that, we need to take some assumptions. 1 minute. Okay, sorry for the interruption. And for the assumption, we need to take some following assumptions. That is, first one is the material should be isotropic and homogeneous. That is, you have already known that isotropic materials are there and homogeneous materials are there. And the question is asked in your series question paper as well. So no further explanation required. The material should be isotropic and homogeneous. This is the first assumption. In your notebook, you have 7 assumptions. You can follow that thing. This is explained detailedly. So there may be some extra assumptions. No need of considering that. You can follow your notes. You have already written in your notebook that what are the assumptions of pure bending. And very important thing is the second one, the beam is initially straight and unstressed and all longitudinal filaments bend into circular arc with a common center of curvature. When we are deriving equation of bending, we need to take the curvature or center of curvature. So the assumption is the beam should be initially straight and every layer is of its free to expand on every direction, constant. That is the important thing. And very important thing is third one, the elastic limit is never exceeded during the bending. That's very important thing. The stresses should be within the elastic limit. That is that meaning. All the stresses should be within the elastic limit. And Young's modulus, that is, you already studied what is Young's modulus. This is strain, stress-based strain, which is a mandatory term in simple bending. So, Young's modulus for the material in compression as well as tension should be same. That's an important assumption. If you are considering tension as well as compression, the Young's modulus should be same for the material. And another assumption is the transverse section which were plane before bending remains plane after bending also. So the transfer section, that is the secondary section, that should be plane before bending and after bending. This is important because we are taking moment of inertia into consideration of theory of bending. So it's a very important term. Okay. Then next one is radius of curvature is large compared to the dimension of cross section of beam. You can see the image in the next slide that when you are taking a radius of curvature, that is capital letter R, that should be far bigger than cross-sectional area. Or radius of curvature is very large compared to depth of the beam. That is a simple term. And next one is there is no resultant force perpendicular to any cross section. It's very important point. And also the cross sectional area is symmetric about an axis perpendicular to the neutral layer or neutral axis. And these are the important parameters to be or assumptions to be made for the simple bending. Okay. And the last point is not much important because we have not included this in the notebook. In most of the textbook, this is not given that much importance, even though this is an assumption. All the layers of beam are free to elongate and contract independently of layer above and below it. That is, there is no constancy. That is, the layers are free to elongate and contract whenever they want, and that is independently moving. That's the important assumptions. So now we are going to discuss what is simple bending or theory of simple bending. We have already discussed simple bending, that is the elemental area or length of the beam where shear force is zero and bending moment is constant, then that is known as simple bending or pure bending. So now we are going to discuss theory of simple bending. For that, we are going to take a section. This is the initial section. As we have mentioned, assumption that the initial section should be straight line. But in our notebook, this not be the terms used may be different because that is, I think A, B, C, and D, as well as this neutral layer be taken as EF and this layer taken as GH. So just consider that thing. There is a change in our notebook notations and the explanation. And when you are taking a bending moment, you can see that we need to take a material and we need to take two sections, that is AB and CD, and the neutral axis is denoted by NN, and you need to consider a small distance y from the neutral axis as GH. That's an element. So if you are considering that and the length between AB and CD will be dx, then applying bending, simple bending, automatically this will bend down. You can see that this is bending. So you can see that the neutral axis is bending about radius of curvature R. The point of radius of curvature is denoted as point O, and the angle is not Q, that is theta or phi. Normally we will take it as phi. 1 minute. Normally we will take it as phi. So this length will be changed. This is an important theory and a very important figure. You need to note down all these things. And importantly, the distance between neutral axis and EF element will be y, small letter y. These are the important terms, and you can also see the stress diagram, and you must be very understandable that the tension and compression are the reason for bending stress mainly. So when you are applying a load, you can see that this will become curve. So definitely if you select a elemental area here, this will be under compression. This elemental area will be under compression, and opposite side when you are taking this side, that is here we are taking a elemental area, this will be under tension. And when you are looking the figure at the neutral axis, the compression and tension will be 0. So at neutral axis, the stress will be 0. So maximum compressible stress at the section A dash C dash and maximum tensile stress at the section B dash D dash. This is the basic equation. So now we are going to discuss how to derive this one. For that, you need to take into consideration that the neutral axis, that is 1 minute. The neutral axis n dash nn nn will be same after and before. You can see that there is no stresses acting on the neutral axis. So if there is no stress acting on the neutral axis, mean definitely n bar n will be n dash hyphen n dash, right? So you need to find a relation for this length, that will be nn or n double n dash n dash. That will be when you are looking the figure. If you are substituting this as phi, then that will be r into phi. R into phi. This will be the neutral axis relation. And now you need to consider strain in the EF. That is the element we have chosen here, that is EF. So we need to consider the strain, that is strain equal to, what is strain? What is the basic equation for strain? What is the basic equation for strain?
Delta L by L.
Tell me.
Delta L by L.
Yeah, that is delta L by L. That's the basic equation. Delta means, sorry, I'm writing the code, capital one. Instead of that thing. That is delta, small letter or capital letter, that you can use delta. Capital letter means that will be a triangle. So delta L by L. Change in length divided by original length. This is the basic equation. So we must know what is change in length. So finding change in length, that will be the difference between final length and initial length. Final length minus initial length divided by initial length will be the bottom side. That is the length. So when you are taking final length, that will be, what is the final length? E dash F dash, right? The final length will be E dash F dash minus initial length will be here, that is EF. Initial length will be EF divided by EF. You can take your notebook, you can compare the relation, because in the notebook the terms are slightly different. So when you are writing, better you study based on your notebook. So this will be our relation. And when you are taking the values, that is EF is equal to, when you are looking this figure, EF is equal to NN. Same, right? There is no difference. EF equal to NN. But here there is a change, that is there will be a small increase, that is E dash F dash will be What will be E dash F dash? If n dash is found by the relation r into phi, similarly you can find the relation for E dash F dash. So that will be r plus y into phi. That is, when you are taking the relation for E dash F dash, that will be R. Till now here, that is R. There is another term Y from here to here. So R plus Y will be the length into phi. So EF will be R plus Y into phi. This will be E dash F dash. And we have already mentioned that this term will be the EF, since n is equal to EF. So we have both the equation for E dash F dash and EF. So you can substitute the relation. When you are substituting the relation, that will become R plus Y into phi minus R into phi divided by R into phi. This is the basic equation for us. And you can see that both terms having phi on the top. So you can cancel it one. So the final equation will become R plus Y minus R divided by R. This will be the relation left, and there is a positive R and negative R, and final equation will become Y by R. That is, what is this strain? Eta equal to, sorry, epsilon is equal to Y by R from this equation. But we have already from Hooke's law, stress strain is equal to epsilon is equal to sigma by E. This is the basic equation for strain according to Hooke's law. That is, stress by strain is known as Young's modulus. So stress by Young's modulus should be equal to strain. And when you are substituting this equation, you will get sigma by E is equal to sigma by E is equal to Y by R. Sigma by E is equal to Y by R. And when you are looking the equations, this is a very important equation. So I am taking it in a bracket and putting it as equation 1. And when you are looking the equation, you can see that sigma by E is equal to Y by R, which is the first side of bending theory. And now we need to find the second side. And what is the time?
10-13
എത്ര മണിവരെ ക്ലാസ്?
20.
20, okay. We have time. No issue. So when you see that Young's modulus E is constant and R is constant, then stress is directly proportional to Y. That's why in the previous case, when Y increases, stress also will increase in both sides. The Y is the distance between neutral axis and the element. So at neutral axis Y will be 0, so stress will be obviously 0. And when axis increasing, that is Y increasing, automatically stress will be increased, and at the top as well as at the bottom, the maximum stress occurs. So from this relation you can understand that. So for finding the next term, that is second equation, you need to consider a small elemental strip. 1 minute, I will consider that thing. You need to consider a small elemental strip with neutral axis, and you need to take a small area, that is, this area will be delta A. Small letter A enough, I have written like that. So when you are taking this distance, this will be saying that y, consider a strip of area delta A, that's a small area at a distance y from the neutral axis. And we have already equation for stress as sigma equal to E by R into Y, right? In the previous page, we have derived the equation as E sigma by E is equal to Y by R. From that, when we are taking E in the right hand side, that will become sigma equal to EY by R. Okay. And the force action, that is when we are considering a force acting at the elemental strip. When we are considering a force acting at the elemental strip, that will be dF will be what is force? Stress into area, right? Stress into area, that is delta A. Delta A. And you can substitute the value of sigma here, then that will become E by R E by R Y into delta A. And you can find moment of the resisting force about neutral axis. If you are finding the moment, that is dm, if you are finding the moment, and if you know the force, we have a relation. Shear force into when relation namakariam, we have a relation that df into perpendicular distance, that will be y. df into y. When you are substituting this one, you can see that this is df, and you can substitute y, then that will become E by R. Already there is a y, and now we are multiplying y, so that will become y square delta A. Y square delta A. So this is for an elemental strip having a area of cross section delta A. If you are considering all element, that is complete element, the moment will become integral E by R y square delta A. Or you can see that Young's modulus is constant for a material for tension and as well as compression, and radius of curvature also will be a constant value, and it is a very large value compared to the depth of the beam. So you can take both those terms outside, then equation will become E by R, E divided by R into integral y square delta A. And importantly, integral y square delta A is a term which is known to us from engineering mechanics. എന്താണ് integral y square dA?
Moment.
Yeah, that is area moment of inertia. So this will become E by R divided by capital letter I. So M is equal to E by R into I. And we are substituting this one in a form that will become M divided by I is equal to M divided by I is equal to E by R. E by R. This will be the second equation. This will be the second equation. And when we are comparing with the previous case, there is a small change required. That is, in the upcoming problem, the terms coming is E by R. So you need to rearrange this one. That is, sigma by Y is equal to E by R. Right? A small change, that is sigma by, you need to just change over this data. That is sigma y is equal to E by R. So when accumulating both this equation, you will get sorry, accumulating both the equation, you will get M divided by I equal to E divided by R equal to sigma divided by Y. This sigma can be expressed as F also. In some problems, we will take it as F. So this is the basic bending theory. And when you are calculating, this theory also known as bending formula, flexural formula. That's the important thing. This is also known as bending equation and flexural formula. So in question paper, they may ask what is flexural formula. And this is for today. This is the basic equation. For studying this equation, we have a small word that is you need to write in this fashion, not like this. That is E divided by R equal to M divided by I equal to F divided by F means stress Y. So for studying or remembering a code word, we are rearranging this one in this manner. That is E by R can be expressed as Elizabeth Rani, may I find you or follow you. Elizabeth Rani, may I follow you. So this is the basic equation or theory of bending or bending equation or flexural formula. Thank you for listening, and please write your attendance in the comment window. Please put your attendance in the comment window. You can leave the class now. If anyone pending to submit remedial class as well as assignments, we do the needful because I am going to submit the marks.
ഹലോ സാർ ഇന്ന് സബ്മിറ്റ് ചെയ്യുന്നല്ല ഒരു ഹോസ്പിറ്റൽ കേസിലേക്ക് പോയി
കുഴപ്പമില്ല, ഇന്ന് വൈകുന്നേരം വരില്ല, ഞാൻ കൺസിഡർ ചെയ്യാം.
വൈകുന്നേരം വരിക?
ഇന്ന് വൈകുന്നേരം വരെ സമയം തരണം. എന്തായാലും കൂടുതൽ വേണമെങ്കിൽ പറ.
ഒരു രാത്രി വരെ ആക്കി തരുമോ?
ഓക്കെ, രാത്രി ടൈം 11.
ആ മതി.
ഓക്കെ, please put your attendance.